So we've been talking about planes, and you have this idea of a plane here, and what you might want to know, if you have some sort of generic point in space, you might want to know how close it comes to a plane, or what the distance is to a plane. Now, why would we do this in practice? Well, in practice, what you're going to have is you might have a trajectory of a line. So some sort of object is traveling along some sort of trajectory, and you might want to be able to figure out how close it's going to get to some object. So you might think of an asteroid is passing near the Earth. How close are those things going to get? And the mathematics on doing that is a little more complicated, but the fundamentals on how to do that are here. They're all extensions of doing something like this. So if I have a plane, and that plane is defined by some sort of point and some sort of normal vector, then the easiest way to figure out how to get the distance from that point to that plane is over here. But let's talk a little bit about where that value comes from. So if I have some sort of point Q, then since the planes extend forever, I can think of, just if I had some sort of string, right? I could just drop it from Q, and it would land somewhere in the plane. Assuming it was all gravity, whatever, it doesn't matter. But it would land somewhere in the plane. But the problem is, if I pick some point in the P, I can't guarantee that P is the point that minimizes that distance, right? I'd have to just keep guessing. Is that right? Is that right? Is that right? You'd be there till the end of time, right? So let's use what we know about, what we've learned about things like projections, to kind of be clever about it. So what I see is that height difference, well, if that point went straight up from the plane and touched Q, right? No angle. If it didn't go off an angle, it went straight up and touched Q. Well, then this vector from this point, this unknown point to Q, would be orthogonal. So it has to be parallel to the normal vector. Has to be. Why is that important? Well, that means that this vector is the same as this skewed vector projected. So if this vector was projected on the end, it would be the exact same height. But this vector projected on the end has the same height as these two vectors. So by knowing that the projection of this vector onto the normal is the distance we want, we can say, oh, well, that's just the projection of V onto N. So all I need to do is get the magnitude of the projection of V onto N. Well, then if I do that, then a little bit of math, I would strongly suggest thinking about what this is and figuring out why it's the same as that. Remember, the projection always produces a vector, but we're getting a number here. So you might want to think about why the magnitude of that projection comes out as this. So we're going to discuss an algorithm, a quick way to get there, but the short and conceptual understanding is that you take the dot product of any point in the plane, the directed line segment from that point to Q, you take the dot product of that with the normal vector, take its magnitude, divide it by the magnitude of the normal vector, and then you're done.